Okay, so first we need to define the coordinate system, and for this example we're going to use cylindrical polar coordinates. Next, we need to define the material coordinate transformation for dyd material, and after you've done that, compile the model by selecting double precision. Next, select basis under the mesh menu and choose a 3D linear Lagrange basis function and press add. Hit OK to exit the menu. Next, we need to define our nodes for the model. So open the node menu and insert nodes until you have a total of 8. Then first, we'll just go down each node and define its position by its x, y, and z coordinates. Now that all of the nodes are defined, go back through the list and rename them in order as inner proximal 1, inner distal 1, outer proximal 1, outer distal 1, and so on. This will be helpful later when applying boundary conditions. Next, we need to define the elements. Open up the elements form and input values as shown. Now that our mesh is defined, select Send, Calculate, and then Render Nodes. Select Undeformed in the rendering menu. Next, select Render Elements and click Render. Now that we have a model, we need to refine it for accuracy. Go to Mesh, Refine, and decrease the elements in the x1 and x2 directions, and increase the elements in the x3 direction. Then Send, Calculate, and render the new nodes and elements. Next, select Biomechanics, Edit, then Constitutive Model. Begin by selecting Import and import the constitutive model file that can be obtained from the Continuity Library database. After doing this, expand all the subgroups and we're basically required to fill out its components. Begin by defining the exponential term of the strain energy function Q. Notice that the parameters for Q automatically appear once Q is defined. Next, add additional output variables by right-clicking. Each of these variables will be defined in this example but which outputs you want are ultimately up to you. After finishing defining an output variable, make sure to select yes when asked if you want to replace the equation with the template. Next, define the Q parameters, stress coefficient, and bulk modulus based on values found in literature. Then compile the constitutive model with double precision and close the window. Now, we will set up the boundary conditions. Begin by first updating the model's initial conditions with undeformed nodes. Then open the boundary conditions menu and select deformed coordinate 2. This will apply deformation for the theta direction. Insert 4 nodes and rename them as dot star proximal 1, dot star distal 1, and so on. Because we defined each node with these labels earlier, we can conveniently apply boundary conditions to groups of nodes, especially when refining the mesh produced almost triple the amount of nodes we normally had. Because we are holding one set of nodes fixed and closing the other, we will only apply a deformation of about 58 degrees here in radians to only one set of nodes. Then select deformed coordinate 3, or the z direction. Similarly, insert 4 nodes and rename them. But since we want to fix the model in the z direction, we will leave all values at 0. Then select the external pressure tab and define an incremental pressure of 0.4 on the inner surface. Before proceeding to solve the model, check that the model dimensions are correct. Click on Apply Marked Recommendations and exit out. Next, click Send and Calculate. Then open the nonlinear solver. Change the time step to 0.1 and the number of steps to 10, and then click on Solve. As you can see, the solution converged, and so now we are able to view the results of the deformation. Render both the deformed nodes and the elements. You can then change the color scheme of the model by going to View, Show Open Mesh, and changing the RGB values in the Color tab for selection in the list. We can now add a color gradient representing the results by first rendering the deformed surface. Next, go to Biomechanics and select Render Surface. We'll place the gradient at the midpoint of x2. Then we'll select the deformed output. And finally, we'll select the second Piola-Kirchhoff stress at the 2, 2 coordinate.